Friends, welcome to the next lecture under the heading of Basics of Machining. In this lecture, we will try to cover milling. As we have seen already, the fundamentals of a single point cutting tool, the geometry which are involved in single point cutting tool, the type of chips which is produced by single point cutting tool, then little bit of force analysis we also went through in the previous lectures. Now, we will move towards multi-point cutting. So, multi-point cutting, as we have already dealt very little, saying that there will be multiple tools engaged for cutting. So, milling is one common machining process which falls under multi-point cutting. In this lecture, we will try to see little bit introduction on milling, then types of milling machine, then parts which are involved in milling machine. Some of them will be similar to that of lathe, but here milling machine, the workpiece is constant, the tool rotates. So, naturally there will be different parts which are involved in milling machine, then work holding devices, different types of milling cutters, milling methods, and then we will try to see some of the operations which are commonly done for milling, and then finally we will try to have a recap. If you see this video, it clearly tells you that a cutter is going around on a fixed workpiece. So, the cutter rotates at a very high speed, you are not able to clearly distinguish multiple cutting points. And here if you see, there are chips which are produced, majority of the chips which are produced are discontinuous chips as compared to that of your lathe machine where you had continuous chips while machining ductile material. Why is this phenomena happening? Because the first cutter and the next cutter comes in contact with the same place. So, you will try to have slightly longer, but smaller chips. And here it is also interesting to see the milling cutter face is trying to machine and create a slot on the workpiece. And here it is trying to create a circular trajectory. It moves in a circular trajectory and you are able to get it. Milling is a machining operation in which the work part is fed past a rotating cylindrical tool with multiple cutting edges. So, suppose you try to have a cutter like this, here you will try to have multiple cutting edges which are coming in contact with the workpiece. The axis of rotation of the cutting tool is perpendicular to the direction of feed. This is very generic. Today you have horizontal, vertical, inclined. So, this need not be true, but majority of the time it is true. The axis of rotation of the cutting tool is perpendicular to the direction of feed. This orientation between the tool axis and the feed direction is one of the feature that distinguishes milling from drilling. We saw drilling operation using a lathe machine, wherein which in the tailstock we mounted a drill and then we rotated it as against the workpiece. So, there the RPM whatever was given is given to the workpiece and the rotation in the drill was done by hand. Here it is given by the machine tool. The milling is one of the most versatile and widely used machining operation after lathe machine. The cutting tool in the milling machine is called a milling cutter. So, this is called as a cutter. So, henceforth the tool we will call it as cutter and the cutting edges are called the teeth. So, this one is called a teeth. So, several teeth. So, each teeth is a cutting edge. In conventional machine tool that performs this operation is called as a milling machine. The control conditions such as milling speed, feed rate and depth of cut are operating parameters in milling operation. Okay, the same thing what we had in single point cutting tool, speed, feed rate, depth of cut, here also it is the same. So, if you see that the tool is sunk inside. So, this is called the depth of cut. So, what is the depth you give, and the rate with which it rotates, this is called as a feed rate, and of course, you will have the RPM. So, here it will be feed rate will be again in millimeter per revolution, or it will be millimeter per minute. Milling is an interrupted cutting operation. So, if you see here very clearly, these are cutters, and each cutter, it has a cutting edge, and this is called as a teeth. So, a cutter is made out of multiple teeths, that is why it is called as multi-point cutting, and in lathe machine you used to get a continuously material removal is happen, but here it is always interrupted cutting. So, interrupted cutting means at every time it cuts, then next cuts, next cut. So, there is always a phenomena of vibration going to be as compared to that of a lathe machine. The teeth of a milling cutter enters and exits the workpiece during each revolution. So, what they are trying to say is it enters when you keep moving. So, if you see here it enters for cutting. So, there is a chip which is removed. After the material is removed, the teeth is exited. The interrupt cutting action subjects the teeth to a cyclic impact force and a thermal shock on every rotation. Why is the thermal shock? There is a friction phenomena between the metal workpiece and the cutter. There is a friction phenomena. In single point cutting tool, the tool edge was continuously in contact. Here it is going to be after it enter, it exits. So, there is going to be a discontinuous contact. The temperatures will be very high, but the teeth will also have time when they are going on the idle cycle, they will not come in contact with heat. So, they get cooled. So, basically because of this action, you will not have tool wear so fast as compared to that of a single point cutting tool. The tool material and the geometry must be designed to withstand these conditions. So, the tool will generally be made out of HSS because that gives you the toughness property. Today, we have inserts also. So, there are small inserts which are inserted at the cutting edge and they come in contact. These inserts are attached to a cutter, wherein which this rest of the portion will try to take care of the toughness property. When we look into a typical milling machine, this is how it looks like. Lathe machine, we saw that it was horizontal. Here I am trying to explain a vertical machine. So, it is classified into different categories depending upon the construction, specification and operation. So, construction is vertical axis. You can also have horizontal axis. Milling machine horizontal is also possible, but here we are trying to take the vertical axis. Moment you see the vertical axis, next point comes is how do I specify the machine? In lathe machine, we try to say the distance between the head stock and the tail stock and the swing diameter. That is the major thing. Here also we will try to see what are the specifications, and then of course, we will try to see operations. So, here you can see there is a column and a knee type. A column, this is a vertical column and a knee type. So, as though there is a knee here, then hand milling machine, then plain milling machine which is horizontal, then you have universal milling machine, then omniversal milling machine which is universal, omniversal milling machine, and we have vertical milling machine. So, these are the different types of milling machine. In lathe machine, we saw engine lathe, tabletop lathe. So, like that here also we see all these things. Manufacturing of a fixed bed type, you have simplex, duplex and triplex type of milling machine. Manufacturing of a fixed bed type. So, the bed is this. This is the base and this is the bed. So, plain milling machine or horizontal milling machine. In horizontal milling machine, this is the front view and this is a side view. You can see the cutter is mounted horizontally, and here this is the machine vise where the work is held rigidly. So, now the table can go up or the cutter can come down, and then it will come in contact with the workpiece to remove material. Depending upon the angle you place the vise, you can try to have taper or you can try to have a straight slot possible. Okay. So, the height of the table can be adjusted by vertical transverse handle, and if you want to have this motion, so that can be done by a cross transverse handle. So, one is depth height wise and the other one is x, one direction you can try it can be x or y, it can be in this direction. So, that is also given here. So, you have a same freedom like that in lathe machine, here also you have this cross slide. So, cross traverse handle is there. So, you try to rotate it. So, then this portion moves. The cutter is held in a arbor. The arbor is used to hold, and this arbor is attached to a spindle wherein which it is attached to a spindle wherein which the RPM, the motor is attached to it, and here are that gearbox levers. You can try to get multiple combinations. The arbor has to be held on the other side, otherwise it will be like a cantilever type, the deflection can happen. So, you are holding it. So, that holding it is done by a overarm. This is a typical horizontal milling machine or a plane milling machine. So, the table can be adjusted in 3 directions: longitudinal, cross and vertical. So, you try to get x, y and z movement. You can try to have any 2 movements. Depending upon the 2 movements, you will try to get a taper. The longitudinal movement, it occurs when the table shifts at the right angle to the spindle. The cross movement is achieved when the table moves parallel to the spindle. The vertical is adjusted in the vertical plane when the table moves against the cutter. In the horizontal column and knee type milling machine, otherwise simply a horizontal milling machine, you see the following description. Say for example, you have this vertical motion moving up, this handle rotating, right. So, this is the bed base or the bed, and this bed is mounted on a column. So, this is a column, then this column is then housing the cutter. This is a cutter and along with all the adjustments. It is the foundation, base is the or the bed is the foundation of the machine made out of grey cast iron. Grey cast iron, why is it used predominantly, is because it gives you the toughness and it is very hard. It also has a lubricating property. If you go through the microstructure, you can see graphites present along with the material. So, these graphites also give you the lubrication. It also serves as a reservoir of cutting fluid. So, here you can use it also as a tank. Column, it is the main support. This is column. This is the main support of the machine, and the motor and other drive mechanisms are mounted on it. The knee is as though a human sitting. So, this is the knee. The knee projects from the column and slides up and down through the vertical. So, there is a guide, like in lathe machine you also have a guide here. This is the guide. So, this guide tries to restrict it and move up and down. It supports the saddle, part, and then it is able to move up and down, left and right. So, this is a saddle. The saddle enables the side to side as well as in and out in the motion of the milling cutter. It is the intermediate component between the table and the knee. The saddle supports, it carries the table. Now, you can see the table part. This is a table. This is a table and this is the vise to hold, and this is the cutter. And here it is called as vertical cutter, vertical axis cutter or a face milling cutter. So, there are T slots, in the table. These T slots will be something like this. This will be here. These are the T slots which are here, and these T slots are used to hold the vise. There are T slots along the length of the table. Why is that T slots along the length of the table? It gives you infinite locating positions. If it is a hole, if there are holes done, then there are fixed discrete points. When you have a long lengthy T slot, there is infinite locking positions. They are T slots along the length of the table for holding the workpiece. The table rests on the guide and the saddle and the longitudinal travel in the horizontal plane. It supports the workpiece, fixture, etc. Workpiece is on the top, the workpiece is held in a fixture, that is a vise. The overarm, as I have already told. So, if you see in the arbor, you are placing the cutter. So, now from the end to the cutter, whatever cutter location, here you will have spacers. These spacers are used to move the cutter along this axis and locate it at a point where you want to exactly machine. The other way around, here also what will happen is the cutter should not wobble or deflect. So, we protect it again by putting a spacer. So, these spacers try to locate the cutter with respect to the workpiece. The arbor is an accurate machining shaft. This is the accurate machining shaft. The cutters are mounted on the arbor, which is rigidly supported by a overarm. This we have already seen. So, now here in this arbor, you will also have the other end here. You will have a taper spindle locating point. So, here you will have a cutter or the arbor which is located. So, it is a taper and at one end to fit the spindle nose, and it has two slots to fit the nose keys. These are the slots. You will have the opposite side, the nose keys for locating the driving edge. This is the vise. The vise can have only up down movement or left right movement. If you have a proper setting and have a gear meshing, you can also have a swinging around. So, that means to say it can move up and down, left and right. This is easy. But now, if you want to orient at an angle, so then we have a wheel which is a handle wheel which rotates, and the vise gets meshed on to a gear. It tries to rotate and you can fix it at angle. So, what is the freedom? It tries to, suppose you want to make slots like this, it is possible. You want to make slots like this is also possible. All these things are happening in one plane. In one plane you cut. But now, there is also a possibility you can tilt it. You can tilt it like this. You can tilt it like this. So, that is called as the universal vise. So, here you see that this option is also given to the vise such that you can get the taper also. So, swivel vise and universal vise. Let us understand universal vise. Universal vise can be tilted in horizontal and vertical plane. Over the horizontal swivel base, the vertical swivel arrangement is provided. It is used to tilt the vise body to a certain degree. So, this one as well as this one is possible. There is also an indexing head. This is used to make a taper, right? Taper in one axis or two axis. Swivel is around a single plane, you rotate. When we try to look into indexing or dividing head, so where do we use it? We use this when we want to make a gear, or if you want to make slots. You want to make slots, you will try to have an indexing mechanism. So, what is the function of the indexing mechanism is, you will try to rotate, the workpiece rotates in a fixed or to a fixed angle, and then you hold the workpiece. Now, you rotate, you still, you rotate, you still. Now, when you rotate and still, what happens at that plane, you can try to do operation. Suppose if there is a cutter which is supposed to make a straight groove. Now, I index. So, a cylindrical part can be made into a square by having this indexing mechanism. A gear can be cut by using this indexing mechanism. In index also there is a indexing plate. So, in the indexing plate there are multiple holes, and then you have a crank to locate it, rotate it and locate it. So, then this indexing head plate will transfer the data to indexing head. From the head it will transfer the data to workpiece, and the workpiece rotates. Here the workpiece is held between two centers. These two centers are called as like tailstock and headstock you can have. So, tailstock is a dead center where there is no RPM given. Here you again it's also, this portion is also a dead stock, you rotate it and then you stop it. So, it is a device for dividing the periphery of the workpiece into any number of equal divisions. This has to be uniform. For example, the angle between these two can be 30 degrees. It has to be uniform all around 30 degrees. The process of dividing the periphery is called as indexing. This is very much required. If you want to have a hexagonal bolt, if you want to convert a cylindrical to a square, this indexing mechanism is required. If you want to cut a gear, it is required. The indexing head has a headstock and a tailstock. The workpiece is held between the headstock. This is the headstock, this is the tailstock. The short workpiece are held in a chuck fitted with the headstock spindle. The longer one is held between the headstock and the tailstock. Arbor. There are several types of arbor. So, the major one is a standard arbor and a stub arbor. This is the standard arbor. So, you will have a key which tries to lock, because when you have a spacer it is cylindrical. When you have a shaft it is also cylindrical. Now, these two, the cylinder has to, the hollow cylinder has to be arrested when it is resting on top of a shaft. So, here what we do, between the two we will have a key. So, the key makes sure that there is a positive locking between the spacer and the shaft. So, that is what is the spacing collar, and then you have a nut. So, standard arbor having a center bore are mounted on a standard arbor of a milling machine. The arbor has a shank which is always a taper. This is called as Morse taper. And here what will happen is you will have a self locking mechanism. You will have a self locking mechanism, that is why the shanks are taper. And the top end of the shank will be attached with a nut and bolt, so that it gets properly fastened to the machine tool. A shank has an internal thread. The draw bolt, a draw bolt holds the arbor in position. The draw bolt is introduced into the spindle bore from the back end of the, this is the draw bolt, from the back of the milling machine column. The draw bolt is used to pull in and push out the arbor from the spindle, so that you have a positive locking. Stub arbor, these are small arbors, short arbors. Its construction is very similar to that of a standard arbor. So, a shank, there you had a draw bolt. So, here you have a small, very similar to that of a draw bolt you will have. So, that is used to hold the shank to the machine tool. The taper shank fits into the taper hole of the spindle. The draw bolt are used to pull the arbor tightly and hold the workpiece. So, this is the draw bolt, this portion. The flange of the arbor is clamped to the spindle nose to give a positive drive. One or two spacing collars are used to set the cutter in position. The clamping screws may be used to fit the cutter in the arbor. Then we have adapter. These are all arbor, right? Then we have an adapter. Many cutters have taper shank. This is an adapter. Okay. So, there they have a taper hole. Shank also has a taper hole. This also have a taper hole. So, to mount this adapter to the machine tool, we will always have a slot to engage the dog, so that you have a positive drive. So, this is used. So, many cutters have a taper shank. It has an internal taper hole to receive the taper shank of the cutter. Then it has an external taper. Internal taper is also there, external taper is also there to hold it into the machine tool. So, basically the cutter comes here. You also have spring collets. See, these are all mechanical hard solid collets. Spring collets, they are little fragile. So, what happens is, here you have cut grooves on a cylindrical part, which has, where the material will have lot of elastic limits. It will have little bit of expanding and contracting. So, now you push the tool inside, the tool is pushed inside, the split jaws expands and then it locks. So, those things are called as spring collets. Spring collets are also used. When do we use spring collets? When the diameter of the cutter is very small, we go for spring collets. Otherwise, we go for adapters and arbors. There are different types of milling cutters. So, we will see them. One is called as the plain milling cutter. So, in plain milling cutter, this is the cutter. So, you have a width of the cutter. then you have the diameter of the cutter, which is important, and then you will have a center portion of the cutter, which is used to locate himself with the arbor or goes inside the arbor. Then you will have, these are all tooths. These are all tooths. So, now what you do is you try to hold the cutter and then rotate it. So, you try to get a flat or a slot output. When we have a slab milling cutter, the slot size, the groove, whatever is getting done here, it can be small. When you want to make only a flat plain surface, then we go for a slab cutter, where in which the width is slightly wider. And here you see there are helical teeths. You can also have parallel teeths and helical teeths. These helical teeths will give you an effect of smooth coming inside and going outside. The straight cutting tools will have an impact at regular intervals of time. Okay. So, you can have a plain teeth or helical teeth. In slab, the thickness is larger. The finishing cutter, which has more number of teeth for the same diameter, the plain milling cutter having the width more than the diameter is called as the slab milling cutter. There are also side milling cutters, which is used to mill the sides. So, if this is the workpiece, so you are trying to cut. So, the side, this is a side portion, the side of the workpiece is removed. It has a cutting edge on the periphery and also on the side. So, it can cut this direction as well as this direction. This cutter is used to remove material from the side of the workpiece. It is also used for cutting slots. Next comes end milling cutter. This is all the three things are for horizontal, this is for vertical. End milling cutters are for vertical, you can rotate it, and here the flat end portion will come in contact with the workpiece to remove, and also the side, which is used for cutting. The end milling cutters have cutting teeth on the end as well as on the periphery of the cutter. It is similar in construction to a twist drill or a reamer. These cutters are generally provided with shank on one side. You have angle milling cutters. So, all cutters which have their cutting teeth at an angle to the axis of rotation is called as angle cutter. So, this is an angle cutter. Some angle is there. So, this is used to cut V grooves, notches, dovetail slots, reamer teeths, etc., etc. So, here there is an angle on the base of the cutter itself. That is what we say angle milling cutter. We have also T-slot cutters. T-slot cutters are basically used for such profiles to be generated. So, you cut from the side and go all along. So, they are called as T-slot cutters. They are also very efficiently used. So, we saw plane, then slab, plane is small, slab is large width, then we have side, then we have end, then angle, then T-slot. So, these are some of the types of milling cutters. When the milling cutter becomes very small, it is called as the saw. So, the saw is used to cut the piece, or it is used for parting the piece, splitting it. So, the thickness can vary from 0.5 millimeter to 5 millimeter, that is the thickness. So, basically wood and all we do sawing operation. Okay. They are used for cutting deep slots and parting of operations. These cutters are thin at the center than edges, providing clearance and reduced friction. So, we are talking about here the teeth will be sharp, and then the teeth when it cuts it also has friction. So, we will try to reduce it, we will make it thin, so that lot of the other portion apart from the teeth does not come in contact with the workpiece. Fly cutter is also an interesting thing, where we make a single point cutting, it rotates and it goes around. It rotates about its axis and also it rotates about the other axis, about the tool axis itself. It is actually a single point tool which is used in milling machines when standard cutters are not available. If you non-standard, right, for example, you might have dia 5, you might have dia 6, but if you want to have dia 5.5 or dia 5.3 millimeter, then we use fly cutters. It is either mounted on a cylindrical body held in the stub arbor or held in a bar. The clamping screws are used to tightly hold the tool, in the above holders. There are also form cutters like what we saw in single point cutting tool form tools. Here you can also grind the milling cutter to a shape what you want to replicate. So, these cutters are classified according to their shape as convex or concave cutters, gear cutters, flute cutters or corner radius cutters. So, depending upon your requirements you can do. You can have a convex, you can have a concave. So, now you know if you want to create a bump on the workpiece, we go for concave. If you want to get a groove, then we go for convex milling cutters. They all fall under the category of form milling cutters. Woodruff key slot milling cutter. So, it is basically used to create a key slot, so that you can place a key for locking. It is a small type of end milling cutter, which is similar to that of a plain or a side milling cutter. The cutter has a straight or a staggered teeth. They are used for making key slots in shafts. So, when we look into milling methods, there are two types of milling methods. One is called as up milling, the other one is called as down milling. Up milling is otherwise called as conventional milling. The cutter rotates opposite to the direction of the feed of the workpiece, it is called as conventional milling. So, you look at it, the workpiece is moving and the cutter is going in the opposite direction. So, here what will happen is the chip will start thin and it will go to maximum. So, what happens? So, there is a gradual entry, then there is a gradual exit. While it is exiting, it takes a larger chip. So, here the forces will start slow and then it will go high for each of the cutter. The cutter rotates opposite to the direction of the feed of the workpiece. In up milling, the chip thickness is minimum at the beginning of the cut and reaches maximum at the end of the cut. The stress on the teeth is minimum at the beginning and maximum at the end. When we go for down milling, it is the opposite. The entry chip thickness will be very large and the exit will be very small. So, here every time the tool undergoes a impact load and then it starts cutting. In this method of milling, the cutter rotates in the same direction of travel of the workpiece. So, down milling. So, it travels like this and the cutter also moves like this. The thickness of the chip is maximum at the beginning and it decreases as and when it goes. There is lot of load on the cutter in down milling operation. These both holds good for horizontal milling. So, what are the difference between up milling and down milling? The up milling is otherwise called as conventional milling, it is called as climb milling. So, the cutter rotates against the feed direction, here along the feed direction. The width of the chip is 0 to max, max to 0. The tool wear is more because the tool run against the feed. The tool wear is less because it runs along the feed. The tool chip falls down in front of the cutter. The tool chip falls behind the cutter. The surface finish is poor, the surface finish is good. So, this is a comparison between up milling and down milling. In up milling, the tool life is less, the tool life is more. So, this is also famous as a traditional way of cutting a surface. This is a non-traditional way of cutting the surface. The high quality cutting fluid is used, a simple cutting fluid is used here. The tool chip are carried away with the help of the tool. The tool chip are carried downward with the help of the tool. The heat is diffused to the workpiece, which causes damage to the metal property. The heat is diffused to the chip and does not change the workpiece quality. Because of the upward force, the strength of the jig and fixture should be very strong. Here it pushes it down, so the fixture can be slightly little lesser strength or lesser rigidity can be there. It requires higher cutting force, it requires lower cutting force. So, generally the milling operations are, this is plain or slab milling, which I told you with respect to slab milling cutters. Then you can do slotting operation, you can do end milling operation, you can have straddle milling on the both sides you can do simultaneously straddle mill, you can also do form milling. So, these are all done with respect to horizontal axis, you can also do it with respect to vertical axis. So, in the vertical axis we have conventional face milling. So, the top face is milled, then we can have partial face milling, we can have end milling for making the slots. Slotting here also can be done horizontal, here it is done by vertical. Then you can do form milling, you can also do pocket milling. So, what video the first time we showed was pocket milling. Form milling is to generate a form outside, pocket is to generate within the workpiece. Then you can also do surface contouring. Surface contouring is possible. So, that also tries to give a pre-form. Suppose you want to make a turbine blade, surface forming can be done. Friends, to recap what we went through in this lecture, we saw the introduction of milling, then we saw types of milling machines, then the parts involved in milling machine, holding devices, different types of cutter, that is in horizontal and vertical. Then we also saw different types of milling methods and various milling operations. These were the reference material which we used for making this lecture. Thank you very much.